Well, today we're going to try to answer the question, why is water bent? Yep, I hope you heard that right. We're trying to figure out why the molecular structure of water is bent. And as a little overview to what's going on here is I'm Ken Braverman. I'm the Excel guy. I do everything in Microsoft Excel. And one of the projects I'm working on in my spare time that keeps me up late at night wondering about the foundations of the universe is I'm trying to build a model of all the way down the atomic structure of everything that we know of. I'm not going as deep as quarks yet, but we're sticking to atoms, and we're going to do atoms and molecules and amino acids and DNA and RNA and cells and eukaryote cells, right? The complicated cells that plants and animals have, and all the way up into a human being, basically. So we're trying to go all the way from atoms to cell structure and gene expression and proteins and everything, and go and make a huge just tree out of it. Well, in order to do that, we need to understand the fundamentals of at least the smallest that we're going to go. In this case, it's going to be atoms. God bless YouTube, God bless human beings for putting out common consensus knowledge all over the internet that we can grab. This is some information I got with the periodic table of elements, and I've put it into a pivot table, which is what I do. And putting stuff into pivot table has allowed me to start really understanding some things about what's going on in the periodic table and how things are bonding. So let's get back to the question here, which is H2O. That is hydrogen, two hydrogen atoms, and oxygen. Those two atoms, they are represented as, here's a hydrogen electron orbital, and here's the nucleus of a hydrogen atom. This is another one. And this is oxygen right here. And the reason, I'm going to show you how we got there. And what we're trying to figure out, this is the question we're trying to get the answer to. Why does it always look like Mickey Mouse ears whenever we say that this bond, this covalent bond, I believe it is, between hydrogen and oxygen always looks something like this, like bunny ears, and it's not something like this, okay? Meaning this is pretty much common knowledge, apparently, that it doesn't do it like this, meaning the two hydrogen, they don't hang out evenly spaced across the oxygen atom. So this thing doesn't spin endlessly left to right or something. It's always at a bent angle. Okay. And so the answer to that question, if you look it up online, is, oh, well, the oxygen atom has a couple of other electrons that are not shared in this bond. And those are tilting or throwing things a little out of whack. And that's why this is a bunny ears connection. This covalent bond looks like bunny ears. It doesn't look more linear or asymmetrical, or whatever you want to call it, right? So I'm thinking, all right, well, I like that answer, but I want to see it. So what we have here is we have this thing called the atomizer that I built. And the atomizer allows you to browse through every single periodic table of element. And what it does is it tries to give you a map of its notation and its orbitals of its electrons, which supposedly have different shapes, which I'm trying to visualize here. And it also tells you things about the atom. It tells you things like the ionization energy, which is amount of energy required to remove an electron from this atom. And there's these four different things we're looking at, three really big ones, actually. Ionization energy, electron negativity, and electron affinity. And the energy about how much energy does it take to remove an electron from the situation, from the hydrogen atom? Well, there's a number here, and it's a measurement number, and it's also color coded, meaning when it's green, it's going to be larger compared to all of the other elements on the table. It's going to be one of the largest ones if it's a green shade. If it's a red shade, it means it's going to be one of the smallest numbers compared to all of the other elements as a sample. So like hydrogen's atomic radius, extremely small, kind of makes sense. It's the first element on the list. It takes a lot of energy to remove that one hydrogen electron that's roaming around because this is a green number. Electron negativity, which is chemical property that describes the tendency of an atom or group to attract upon itself. So this is its how tough its handshake is when it's grabbing another electron. That's what this is. It's electron. Also a big number. So hydrogen wants to grab, apparently. Also, it's grabby. It's a touchy-feely atom. All right. Then there's electron affinity, which is the amount of. Oh, wait a minute. This is its pull. This is its handshake. What's this one? What is this negativity one? Function. So this is attracting to its. Oh, sorry. This is its electrons force attracting to its nucleus. I believe that's what it is. It's how strong it wants to stick around its own nucleus and not move around. I think that's what that means. That's what this electronegativity is. The affinity is how likely it will grab another electron. So it's right in the middle. So we're looking at hydrogen here, right? Well, let's look at oxygen because we're doing water at H2O. Okay. Oxygen, look at that big old huge electron negativity number there, or super green. That is the one that means oxygen, those electrons that are in this shell, which is the P shell, which is the third shell that I've shaped right here. Let me reassemble this oxygen atom so you know what we're talking about. You got a nucleus right here in the middle. You got the first orbital with one electron right here. Okay. Then you got the second orbital with two electrons. That's what it says right here. Second orbital, two electrons right here. And we're going to get into what these guys are doing in a second. And then you've got this P1 here that's got four electrons somehow. All right. Here. And here. Let's add a couple more. So we got four electrons doing a crazy dance around this green orbital and around the blue orbital and all attracted to the nucleus. Okay. So we got some electrons flying around all over the place. But I want to show you what I think is going on and how we can visualize what's happening here. So the problem is that this is not uniform, right? It never looks like this. It always is at an angle. So how could that be? Well, if we start breaking down this whole setup for oxygen, all right, this one orbital right here, which is essentially a hydrogen atom when it's just one here, right? That thing looks like this, right? It's pretty stable. It's pretty strong. Like this electron doesn't want to get moved out too much. So it's fairly stable around that one. Then you bring in this other green orbital here, right? So you got one electron hanging out here somewhere, essentially in superposition all over the place around this nucleus. Then you have two, okay? Well, how do we have two, right? Why is this stable, right? Because the electron's a negative charge. So if it started running over here and hitting this electron, it would repel because like charges repel each other. So these two would be roaming around, having a good time. And then all of a sudden they'd be like, no, I don't like you. And would start going over this way. And then the same thing would repeat itself all over time. So do they own like half of the space? They probably don't own half the space. What they probably do is there is a cloud of energy here. And what is happening is, this is just my theory, is that the electrons are somewhat waves and particles at the same time. And they're hitting the space. And as soon as one moves, you're probably going to get an equal and opposite reaction on the other one to fill the voided space, as they are both equally sucked into the nucleus while also repelling from this other electron that's here in the middle. Okay, right? So they found some cloud where these two are hanging out doing their thing, right? And there'll probably be minor fluctuations. I'm sure there's videos on this and what's actually going on there, but that sounds like what's probably happening. Somebody please leave comments, let me know. So these guys are fairly stable. That's a fairly stable setup. We can look and say, well, which element has, sometimes there's two in a shell. Yeah, helium's the base. Two is actually really strong in this shell apparently as well. Okay, so two super strong. So then we bring in this other orbital shell, right? This one that's looking like an hourglass, it's looking like an infinity, right? And there's 4 atoms roaming around. So here's what's probably going on. Because there are 4 that are doing a dance like this around the atom, also sharing space and reacting with each other, right? Doing stuff like this. Well, when your hydrogen comes along and finally, these two things, their affinities and their negativities and everything, they match up and they cause a reaction and they bond and they start sharing an electron. When this happens, okay, and I guess when 2 happen at the same time, when it picks up 2, it's absolutely going to change this orbital shape slightly. It's going to have to. And the effect of that must be some distortion that whichever 2 it grabs onto, it's going to distort and it's going to create that bunny ears, is what's going to happen. And then these 2 electrons are going to still remain stable and change their orbital paths to something like this to keep the stability of everything. And that's why it's a very stable particle. Let's see if that made any sense. Because there are 4 on the edge of this p orbital, when you lose one, the orbital must shift slightly. And that's what creates the bend. Because we look for this perfect circular symmetry and everything we're thinking of, but there isn't a circular symmetry here. There has to be a bend. So that means that when the bond occurs, that the shift in the orbital is going to lock into an angled manner. And that's why you get bunny ears. I think that's probably why it happens. I didn't know what my answer was going to be when I started the video. Please leave comments below. Let me know if I'm on the right track, because understanding how these orbitals are structured and the energy that's passed around and what happens to these atoms is the fundamental building block to understanding how the amino acids and the bases are structured. Like understanding why C5, H5, N5 is a thing and the shape that it takes and where the energy is coming off of it and what it's pulling relates, because A bonds to T. Like I'm going to figure out why that is. Like, is it these 2 oxygens hanging out? Oxygen wants to pull something, it ends up pulling the nitrogen or pulling the carbon or something. We're going to figure that out. But I think I have an answer of why this is bunny ears, and it's going to be a change in the p orbital shape. Please let me know if I'm onto something. All right. We did learn something today. We did something other than sports algorithms and payroll and all those. We actually did something that that is starting to lay the groundwork to what we're going to do here. All right. Good luck, everyone. May all of your days be educational and knowledge worthwhile.